Right, so finally we've got to the full adder. This is how it actually looks. So this is if you've got three inputs, it gives you the sum and it gives you the carry out. So if there's going to be a carry, again, from three inputs, and if there's going to be a sum from three inputs as well. Obviously the carry-in is from an adder previously, so I'll show you how that works. But I'm going to go over how this is basically made. So as we remember, we've got the sum equation, which is C in XOR A, XOR B. Now, if you look at it, it doesn't matter which way you do it. So A XOR B, so this is an XOR gate. So we've XOR'd the A and B, that's fine, and we've got the answer for whatever that is. Doesn't matter what the answer is, it's just the logic. So we've got the answer of this, and then we need to XOR it with C. So C in goes here, and we've got another XOR right there for the sum. So that's sorted. So that sum is just XOR AB and then XOR with C afterwards, after you've got the output, and that will work. So that's the sum worked out for the full adder. That's the first part. So we've worked out the sum. However, now we've got the carry out, which is a bit more complicated because there's a lot more parts to it. So let's start with the AXOR B. Now we've already got an AXOR B from the previous one here, so we can use this again. So we've used it for this one, and as you can see, it goes down and gets used for this one again. So we've got AXOR B, which we've done. But because it's C-ins on the outside and it's on the Boolean algebra equation, it's times next to it, that means that it's got to be an AND gate. So if it's a dot in between it, like it is here, or it's just times next to it, that means it's an AND gate that needs to be used. So we've got A XOR B and C, which is what this is. So the AND C, so we've got the A XOR B, because you have to do that first, because it's in the brackets. And then you've got AND C, which is there. So that's the AND bit done. So we've done this part of the equation here. This bit's finished. Now we've got AB again, but that's AND because it's A dot B. So A and B, which is here. So this just splits off. You can have wires coming out of that, so inputs can go to different things depending on what they're needed for at the same time. So that's that being done. So with A and B, and then we've got this plus in the middle to worry about now. So the plus is an OR gate. So basically you OR this section, so this section, with this section. So OR that with that to get this, to OR them together and get your carry out. And that's the full adder. That's it. You're done. So that's how a full adder is made from scratch. So you have to do the truth table for it to think, right, how do we solve this problem? What's going to be the truth to it? You then do a Carnot map to figure out what the Boolean equation is going to be, and you simplify that equation. Once you've simplified it, you can then do it on here, like I've done now, and basically work out what the logic gate's going to be. Now, I know that's a lot of information that's just being thrown at you, and we're going to practice this for a couple of weeks just to make sure that we all get it and we understand how this is going to work. So, as you can see, you've got cascade adders. So what you can do is you can put full adders together. So where you've got the carry out for one, this will become the carry in for another, obviously, because it's basically like an equation going through. So you can add two numbers together in a CPU by doing this. This is how a CPU actually does it. So it has adders that go along that are cascaded, so then you can work out what it is. Now, if you were to recreate this is one I made, it will actually add the numbers together. So if you've got, say, carry out of 1 from this adder here, that will carry into this one and affect this next one's calculation, and same for this one, and etc, etc, etc. What I want you guys to do at some point is make this an 8-bit adder, so you can actually put in your own numbers and calculate it. Now, it's easier to use on-off flicky switches, and you can put the switches wherever you want. So it doesn't have to be exactly where I put them on here, so it doesn't have to be there. You can put them down below and say, this is like an 8-bit binary number to add together, and then you can have the output coming out on top. Now, potentially speaking, you don't have to use bulbs to do this. There is a number pad that you can use, which you can put the numbers into, which will give you different numbers depending on what's going into it. So you can use that if you want to instead. It's up to you guys. I don't mind how you want to do it, but I want you to create an 8-bit adder where it cascades. So at the beginning, you can put in two numbers using the flick switches. So put in like say 8 and 9, and it should give you the number 17 out on the bulbs. So it's up to you how you want to do it, but if you've got any questions, please come see me because it is a bit of a tricky concept, especially if you're not into algebra. And I don't mind going over it again because we probably will be going over it in class a little bit more as well. But please let me know if you need anything help-wise for this because it is a little bit complex. But other than that, try and give it a go. Try and make it, and I will be throwing some Carnot map / algebra questions your way at some point just to make sure that you do understand the concept. So, good luck with it, and let me know if you need any help.